Anchors. 1, 2, and where did you hide that one? Third. Right? Using these RCMs. And there are electronics. Some of them were produced by Benjamin from ST while he was a master student in Shomesh. And later we continued that with Thomas and Oscar that has left the project because he had limited employee time, 2 years in Sweden. Yes, so this is the situation today, definitely in some countries, in some cities in Europe. This is a distributed system. And we think that transportation can improve dramatically if we will consider that as a distributed system that can have distributed coordination algorithms. So the future holds a big promise for autopilot capabilities, cooperative, automated driving, and we improve safety, reduce energy consumption, and other important things. But all these current solutions that we are imagining, virtual traffic lights and automatic lane change, we cannot really test them with real vehicles because, and definitely not on the open road because there is so much risk that we cannot remove these risks, or it's very expensive to remove these risks, right? If we want to have the application, to consider applications for the safety kernels on a testing track, we need several millions of euros just to test that with real cars and much longer development. And this is why I thought to have such a test bed where we can test many ideas and show their technology readiness level before we pick up the best one to test in a testing track, in a full-scale case. And this definitely should be the role of research institutes in academia. We have a very uncertain environment. The control algorithm has to deal with uncertainty, but also uncertainty itself. The sensors, the communication, as we talked before, the environment, and the most malicious of all, the user. And still we have to provide high available complex control system. And the question that we are trying to answer is how can we affordably validate the safety properties of this future very large-scale system, right? With a budget that is not of millions and millions and millions, right? These vehicles, they cost around 5,000 korona each, 500 euro each. So that's not a huge expense. If you want to have it a little nicer, maybe 1,000 euro. But that's it. And they were homemade by Benjamin. Yeah, so we can do it affordably and we can demonstrate the ideas. So what are we trying to do? Nowadays it's very modern to test in the automotive. It's very modern to use computer simulation to test and validate the applications. Actually, the entire system. There we use mathematical models to model things like radio interferences. Right? We model the real world. Are there some mathematical assumptions of how the real world behaves? So in theory, there's no difference between these mathematical models and the practice. In practice, there is a difference between these theoretical mathematical models. And in order to reach technology readiness level of 5, we have to use a representative environment. You have cell phones that use Wi-Fi, there's Wi-Fi everywhere. This will cause interferences to our system because we are using normal Wi-Fi. Nothing special about this. Okay? So here, what we did, we designed algorithms. We took off-the-shelf control algorithms for platooning, intersection crossing, etc. And we simulated them digitally. We were trying to do our fault injection digitally to measure packet loss. NS3, we use all the standard models. And when we felt ready, we just took the same code and were trying to go to the real physical world. We couldn't go to a full-scale car because that's a different budget and far beyond our expertise. And therefore, we went to the island of Gulliver, right? Somewhere in between, to help us cross the sea of sharks, of all the difficulties, all the hazards that we will have to move out of the way, the big budget. So we were able to basically design things using a digital simulator, cross the bridge, ride on a physical simulator, and then fix whatever is needed. And we feel this is mature enough to show you today. So we study these opportunities for simulating vehicular systems using both physical and digital simulation. You can do it on a really large scale. So we have 8 cars, but you can have more imaginary cars that produce all kinds of phenomena of stop and go from traffic jams. We have connected it to sumo and etc. So we can test hardware in the loop, but also system in the loop. As you saw in the video, we just put those cars on boxes, and they still communicate with each other, and they move their legs, their wheels in the air, and we are able to test something. And then we also have a physical demonstration of it. So the idea of Gulliver lies between mathematical computer model simulation and full-scale industrial simulations on testing track. It will allow the academia to use a greater engineering task force to participate because it's much more affordable. And also for the industry to have many, many good ideas to pick from which one are the best to use. And also for the government to understand what is possible when it comes to automated driving. What can be beyond the horizon of 5-10 years? There we have the Gulliver test site at gullivertestbed.net that you are welcome to see. What I want to do now is to present the intersection crossing video. So here you see the virtual traffic light where cars are talking to each other and decide who should cross the intersection first. If they have problems with the communication, they might go through some bad rounds, and then it will force them to slow down. But once they have good communication, one will be able to agree with the other and cross. It could be the worst case in which they cannot talk to each other forever until they stop completely. They use their own board sensors and decide how to go using autonomous techniques. So we have digital simulation below and physical simulation above, right? And we have an intersection there. And now we will specify the requirements for a virtual traffic light. At any time, there's only one way that should get a green light, and eventually they should all be able to cross. If the data validity is high, if the data validity is high, they can just optimize the throughput of the intersection. One will just slow down and the other will maintain its speed. So we just saw a digital simulation of that, and here's a physical simulation. They never stop. One is a little bit slowing down, and the other just maintain its speed. Now, if the data validity is low, they will have to both stop because they cannot communicate for some reason. And then they will use their own board sensors to use some other traffic rules to decide who should cross. So you saw the digital simulation of that, and now they will give a physical simulation of that in video. But if Thomas, if you can start, then we can also do it live. So here you see the monitoring of the testbed. The testbed is not controlled by the laptop in the sense that we are sending the instruction how to go. Just the start command and the stop command. And as you can see what Thomas is doing. Okay? So you see now the map, and you see if this is a small circle, they are going high level of service. And from time to time, you will see that this becomes big because of interferences. For example, well, it happens from time to time. But these will be real interferences from the environment that we have. So I hope that soon we will see a real intersection case. Yeah, so he stopped one car. And so we have an intersection where one just continues. Yeah, maybe you can make a more convincing case. And this looks nicer. They are coming, here they are coming, and yes, not close enough. Yeah, he was slowing down. Great. So maybe you can take this car and start injecting packet emissions to this car. Can you inject to car number one, packet emission? Yes. So there are packet emission injected here, but they both decide on a low level of service because one of them is bad. Can you remove the packet emission injection? You are good again. Okay. So, are there any questions about the demo itself? Antonio?
How much you can increase the speed? What is, I mean, what's the maximum acceptable speed in this scenario?
So, they are now moving at 0.5 meters per second. The cars themselves, we tried it to 2 meters per second, but the room is too small. You also need to change the floor to something like that, actually something a little better. Right, but in terms of the electronics, not the wheels that will come off if we go at 10 meters per second, and they will come off. There are no limitations. We haven't met the limitations yet. So the communication rounds are about 200 milliseconds. In fact, we had to increase the distance between the cars because otherwise you don't see the level of, you have to see the difference in the level of service when we go to the tunnel. For that we have to make it more extreme, just like in other demonstrations that we see later. Yes?
So they have no other sensors except for the localization system?
Yes. But, I mean, of course we can add things that we saw in the other demonstrator. That's for simplicity.
For level service of zero, there is still communication? Or
No, zero means, in this demonstration, zero means there was no communication recently. Yeah, so it's either zero because you didn't receive a packet, you didn't receive a message in this round, or because in the previous round, somebody didn't get and he's complained, and you receive his complaint, and then you said, okay, we're going to go with zero a little longer until the communication is good and we are all happy and we go back to high level of service. Yes, so you are bound to have a lateral decision in a bad communication round in the first one. But in any bad communication round that is not the first one, it will be a joint decision, simultaneous. Can you repeat?
Not only one plan, but we can have a lot of vehicle.
Yes.
We can have a combination with 4 or 5 vehicles which are in the given area.
Yes, and we experimented with architecture. So, yes,
If there's no communication,
yes.
then they cannot know the positions